Okay, in our last recording, we talk about basically a distillation tower is like three process combined, using the feed stage as a boundary. Above the feed stage, we have a rectifying session that functions like a absorption tower, in which the liquid stream coming down will absorb the heavy key from the upcoming vapor phase. Below the feed stage functions like a stripping section, in which the upcoming vapor will strip the light key component from the downcoming liquid. Okay? And the fade functions like a single stage flash, which basically fades the fade into this tower. Okay. So when we talk about, basically we need to analyze these three sections separately, then we can put them together. So for the rectifying session, we basically, from the mole balance equation, mole balance, we can derive the operating line for the rectifying session that basically relates the composition of the vapor and liquid phase, right, with the liquid flow rate, vapor flow rate, and the distillate flow rate, which is this. Okay, and then here we define reflux ratio as a ratio of the liquid being returned back to the process compared to the amount that's discharged as a product. Similarly, we also derived the operating line for the strip section based on the mass mole balance. Okay, and we derived the operating line, and we can plot it on the y-axis diagram. So the operating line of the stripping section is a straight line, based on the Maccabi-Thiele assumption. It's going to be a straight line with a slope that's larger than 45 degree line. Okay. So in this lecture, I will talk about the feed stage and how their composition will affect the process, right? And we're going to introduce the concept of Q line. So we talked about, for a distillation column, the feed could be a liquid, a vapor, or a liquid vapor mixture, right? If it's a liquid, it can be a subcooled liquid. It can also be a saturated liquid. If it's a vapor, it can be a saturated vapor. It can be an overheated vapor. Okay, depending on this, what type of feed it is, then and if we look at the feed state, depending on what the feed is, what the feed condition is, there can be different outcome. So if we look at this case where we have a subcooled liquid, right? So the feed is the subcooled liquid entering the tower. So obviously, as a liquid, it's going to join the downcoming liquid that comes from the rectifying section of the distillation column. However, in this case, it's a subcooled liquid, which means its temperature is below the equilibrium temperature. And we assume that in this distillation log tower, each stage is operated at equilibrium condition, which means the feed has a temperature that's lower than the liquid that's leaving the feed stage, right? So as a result, the feed will be its temperature will be raised to the equilibrium temperature, and that energy comes from the condensation of the upcoming vapor, right? So part of this upcoming vapor will be condensed to a liquid to provide energy to raise the energy of the feed. And then this liquid will join the overall liquid, right? So the overall liquid stream will have a flow rate that's larger than L plus F, right? Because of this additional condensation stream. So if it's a saturated liquid, then things become simplified. in which we have the saturated liquid join the downcoming liquid and become the liquid fate in the stripping section, right? Whereas for the vapor phase, it's the same flow rate, right? Because the fate does not provide any vapor. It can be a partially vaporized stream. In this case, the fate is a mixture of saturated liquid and saturated vapor. So the saturated liquid LF will join the downcoming liquid, right, from the liquid stream in the stripping section. So the overall flow rate in L bar will be L plus LF, right? LF is basically liquid flow rate in the fate, whereas the vapor fate will join the upcoming vapor phase, right? Become V. If it's a saturated vapor, then all the fate will join the upcoming vapor. And if it's a superheated vapor, because now the superheated vapor, its temperature is higher than the equilibrium temperature, and then after it enters the fate stage, its temperature will be brought down to the equilibrium. That happens by vaporize some of the downcoming liquid, right? So as a result, L bar will be smaller than L because a portion of the L is vaporized and we will join the upcoming vapor phase. Okay, so if we define Q to be L bar minus L over F, it basically means L bar is a flow rate, liquid flow rate in the stripping section. L is a liquid flow rate in the rectifying section. So the difference means the liquid flow rate change as a liquid flow across the feed, right? And because of the mole conservation, mole balance, and we have F plus V bar plus L equals V plus L bar, right? That means basically, if you look at the fate stage, so you have F coming in, you have vapor coming in, you have L coming in, right? So you have F plus V plus L. When they leave, they become L bar and V, right? So that equals L bar plus V, right? So then if you move L to the right, move V to the left, you have L bar minus L equals F plus V bar minus V. And then that gives you that, right? F divided by F is 1, then you have V bar minus V here. Then we can assign a Q value for each of these scenarios. For subcooled liquid, right, from this inequality, L bar minus L larger than F, so you have Q equals this larger than 1. In this case, L bar minus L equals F, so you have Q equals 1, right? In this case, L bar minus L equals LF. LF is the liquid flow rate in the feed, right? So you have Q equals LF over F. In this case, so you have L bar minus L equals 0. You have Q equals 0. In this case, you have Q smaller than 0. Okay. So that's the definition of Q, right? Tells us basically, depending on the fate condition, liquid flow rate will change as it flows across the fate stage. And Q value tells us how much liquid flow rate changes, okay? And it's tied to the liquid fate, it's tied to the fate composition, fate condition. Now let's look at the Q line, right? So from mole balance, we derive the operating line for the rectifying section, which is straight line, and which is straight line on the y-axis diagram, right? And its equation can be written as this, in which slope is given by L over V and the intercept is given by this term. Similarly, for the stripping section, it's also a straight line whose slope is given by L bar over V bar, and its intercept with the y with y-axis is given here. Now, if we multiply them by V, and V bars separately and the subtract, right? We will have on the left, we have Y multiplied by V minus Y multiplied by V bar. That gives us Y bracket V minus V bar. On the right, we have then X multiplied by L minus L bar plus DXD and minus plus BXB, right? So that is the light K flow rate in the distillate, and this is a light K flow rate in the bottom. Combined together, it's a light based on mole balance. This is a light K flow rate in the feed, okay, FZF. Then we can just divide V minus VF. We can divide F. So that gives us on the left, that gives us this, on the right, it gives us this and that. Since Q is defined as this, right, then if you compare these two equations, we can just replace this term by minus Q. We can replace this term by basically 1 minus Q, right? So you have this, then you can divide this 1 minus Q term to the right. So now you have an equation that relates Y with X, and for given fit condition, Q is constant, right? So this term is constant. So you have a straight line, right? This is called a Q line. So we can prove the Q line is a straight line on the XY diagram, and it crosses with 45-degree line at fit composition, right? Reason for that is that we know on the 45-degree line, X equals Y, and if we let X and Y equals ZF, right? If you plug in that, you will find out the point of XF ZF sit on this Q line. In other words, if you plug in ZF, X equals ZF and Y equals ZF in this equation, it's gonna satisfy this equation, okay? And it ends at where the operating line cross, okay? So here we have two operating lines, each for the rectifying section and stripping section. So they will cross at one point, and this Q line will ends at that point, which means rectifying section, operating line, stripping section, operating line, and Q line, they intersect at one single point. Okay, this is very important. So let's look at this on the figure. Right, on the XY diagram, we have equilibrium line given by the key value. We have 45-degree line, and we have the rectifying section operating line, which is straight line that starts from, this is like, this point is basically the liquid and the vapor composition at above the stage 1. Okay. And this, so then the ratio is given by L over V, right? Or reflux ratio, or L over V, which is dependent on the reflux ratio. And we can draw the rectifying section operating line, right? If we know this point, because XT is given by our desired separation outcome, right? So we have this point, we have the slope given by the reflux ratio, we can draw a straight line. Okay. Now, if we know the fate condition, if it's a liquid or vapor, or if it's a mixture of liquid and vapor, and what if it's a if it's a liquid or vapor, is it a subcooled liquid or it's a overheated vapor? Then we can know Q, right? And if we know the fate composition, we know that point, right? We can draw the Q line. That will basically, then we have that point, then basically the stripping section operating line is determined, right? So because the stripping section operating line is a straight line that goes through that point, and the desired separation outcome point, right? That's basically the mole fraction of the light K in the bottom. So which means then the slope is given, then the reboil ratio is also given, right? So in other words, for Q, VB, and R, we once we know two of them, we can find the third one. Right? In this case, we know the fate condition that gave us this line, and we know the reflux ratio that gave us this line. Then we can find this line and then find VB, right? And the slope of the operating line depends on the fate composition. For a saturated liquid, it's a vertical line, Q equals 1. For a saturated vapor, it's a horizontal line, Q equals 0. And if it's a liquid vapor mixture in equilibrium, it's going to be a value between 0 and 1. It's going to be in this range. If it's a subcooled liquid, then it's going to be Q larger than 1. If it's a superheated vapor, it's going to be Q smaller than 1. It's going to be below this horizontal line. Okay. Now we have operating lines, we have the Q lines. Then we can design the number of stages, and we can also determine where we put the fate stage, right? Remember, the fate stage is where we move from the rectifying section to the operating line to the stripping operating line. Okay, so let's look at this example. In this example, we have the equilibrium line, rectifying section operating line, and the stripping section operating line given. Also, the Q line given, they cross at this point B, P. Right? And we know the fate composition. We know the desired separation outcome, XD and XB. So we know where to start to design the to find out the number of stages, right? That's the starting point. Then we can use the step-off process we discussed for the design of absorption tower here. So we start from this point. That's basically, that point gives you the composition of the liquid vapor phase above stage 1, right? And you move step off horizontally, that will cross the equilibrium line. Then that point gives you the composition of the liquid vapor in stage 1, right? They are in equilibrium. And if you step down to cross the operating line again, that point gives you the composition of the vapor and liquid phase between stage 1 and 2. Then you step off horizontally across the equilibrium line, you can find the composition of liquid and vapor at stage 2, and you do this back and forth, right, until you reach stage 5. So in this example, we put the fate stage at stage 5. Then after stage 5, right, we're gonna, if you further do step down, then you're gonna go into the stripping section. So now we're gonna use the stripping operating line. Then this point will step down, it's gonna cross this point, this line at here. Then you do step horizontally, vertically, horizontally, vertically, and eventually you find out we need a total of 7 stages to achieve the desired separation outcome. Okay. Is this the minimum number of stages we need to use? The answer is no. In this case, we can actually find number of stages, a design with less number of stages to achieve the same separation outcome. Okay. So here in the design of a distillation column, the goal is to basically minimize the number of stages, right? So we can minimize the capital cost. And in a distillation process, if you look at this diagram, right? So basically, when the liquid flows down, the liquid is having a light K composition of XD, right? When it flows down, it's gonna pick up heavy K component from the vapor phase, right? Which means XT, X, that's the light K mole fraction in the liquid, is gonna decrease, right? It's gonna decrease. Whereas the heavier K mole fraction, that's 1 minus X, is gonna increase when we move from the basically, right to left, okay? But we do this not continuously. Instead, we do this horizontally. So you can find out from the top of the tower, when you move across stage 1, you achieve this width of separation outcome, right? That's basically how much the liquid phase composition has changed, when you go across stage 1, okay? And this is how much you have achieved. Your liquid phase composition has changed when your liquid stream go across stage 2, okay? Now, as you can see, basically, in order to minimize the number of stages, we want to make sure in each this discrete operation, we want to maximize this change in the liquid phase composition, right? And clearly, when you move away from stage 3, and we don't actually benefit too much, right? From stage 3 to 4, you're only able to change the liquid phase composition by this much, right? The length of this line segment. And in stage 5, even less, you can only achieve a change in the liquid phase composition from this point to this point, right? This line segment length, okay? So the reason is we're operating our system too close to the equilibrium line, right? Now let's look at another. So in this case, the fade stage is too low. Now let's look at another case. If we place the fade stage at stage 2, right? In this case, then after we step off stage 2, we're gonna enter the stripping operating line, right? So when you do this step off vertically, you're gonna hit the stripping section operating line instead of the rectifying section operating line. Well, similarly, now you can see as you move across stage 2 to stage 3, you don't change the composition in the liquid phase much, right? Similarly, we move from stage 3 to stage 2, you don't change the liquid phase composition much, right? So in this case, the fade stage is placed too high. So in the optimal ideal case, you want to put your stage as close as to the point P, that's the intercross point of the operating lines with Q line. So in this case, you can achieve the same basically separation outcome with only 5 stages, right? Instead of 6 or instead of 7. The reason being that, as you can see clearly, we're trying to avoid operating too close to the equilibrium line. So in each stage, we can achieve a very, very reasonable, right, change in the liquid phase composition, right? This is from 1 to 2, from 2 to 3, from 3 to 4, 4 to 5. Okay, so this is just right. So in summary, ideal fade stage needs to be as near as the intersection P, and this transfer from rectifying the stripping section should happen after the horizontal line cross P, right? So in this case, how do we know stage 3 is optimal, right? Because when I'm doing this step off, right, from this point to this point, you basically cross the P point, the X coordinate of this line cross P point. So that's when I realized I should step down to the, I should step down to the other operating line, which means I need to place the stage 3 here in order for that switch to happen. Okay. Lastly, let's look at 2 limiting conditions. So here we have a distillation column in which we basically return all the condensed liquid back to the tower, right? So that we have D equals 0, L equals R. So the L equals L equals basically, that all the condensed liquid. So R is infinity, okay? And we know when R is infinity, if you look at the slope of the operating line, when R is infinity, the slope is 1. That means this line, it's going to collapse with the 45-degree line. As a result, Q line will become only a point here. And similarly, the operating line for the stripping section will also collapse on the 45-degree line, right? In this case, when you do the step off, you find out you only need 2 stages to achieve the desired separation outcome, right? with only 2 stages, you can change the composition of the liquid phase from XD to XB. Okay. So this corresponds to infinite reflux, and it requires minimum number of stages. And the physical meaning here is that when you return all of your condensed liquid back to the tower, that means you have the maximum amount of the liquid absorbance to absorb the heavy key, right, from the feed. So that's why you only need a minimum number of stages. So in this case, L equals V, right, because D is 0, right? Also, because this line is also collapsed on the 45-degree line, that means your VB is infinity, right? And VB is the Reboyop ratio. That's V prime over B. If it's infinity, that means B is 0, right? So B is 0, B and D are 0, and L equals V. Okay. Another case is so then if B, D are 0, then F is 0 as well. Right? This case is called total reflux. The second limiting case is called a minimum reflux. Right? So in this case, we know previously we talked about theoretically speaking, R can be 0, right? So which means you return 0 amount of the condensed liquid back to the tower, right? So D equals this. In that case, you're gonna have a horizontal line, right? Because R equals 0, the slope is 0. But if that happens, basically, your Q line and your rectifying section line and your stripping line will cross at a point that's outside the equilibrium line, right? That will be something here or even, here, which we know is thermodynamically impossible. So the actual minimum reflux ratio to achieve the desired separation outcome can be actually obtained when you increase L, when you decrease reflux ratio, you decrease the slope. At some point, and this intersection point will move leftward, and at some point it's gonna cross the equilibrium point line. That's when your minimum reflux ratio is obtained, right? So if you look at this ratio, look at this figure, here the operating lines, right? This line and that line and the Q line, they cross at a point that's sitting on the equilibrium line, right? This is a case that corresponds to minimum reflux. Now we have analyzed a similar case previously. When you do the step off, right? Basically, if this P point overlaps with the equilibrium, just sits on the equilibrium curve, then it takes you infinite amount of number of stages to achieve this point P. Okay, so that corresponds to this case corresponds to a case with minimum reflux, and you're gonna need infinite number of stages to achieve the desired separation outcome. So in practice, reflux ratio is going to be between minimum reflux ratio and infinite reflux ratio, so that the actual number of stages is going to be larger than the minimum number of stages, but it's going to be a finite number instead of infinite number. Okay, so we can stop here, and we will continue on next Wednesday.